Hello.
Yep. Good evening, Professor
Okay.
Alicea. Or maybe it's good morning in California.
It is indeed. Well, yeah, sort of good morning still at 10 a.m. here.
10 a.m. Oh my God, it's already 6 p.m. here for us. So we're gonna have a beautiful end of the week.
I'm sorry?
I just want to say that it's a nice end of the week. Nice way to finish the.
Oh, okay. Cool. Well, yeah. Well, thanks for having me here.
Oh, thank you for joining.
Actually, how does this work? So will we just have a bunch of people join for live?
Yes, I think so. But this is a Zoom webinar, so they wouldn't have. So they would have very restricted opportunity to speak. For example,
I see.
they will be able to ask questions in text, and sometimes we can grant them rights to speak.
Mm-hmm. Yeah, so I mean, I will definitely encourage questions. Now, on my computer, it may be difficult for me to actually see when questions appear.
Mm-hmm.
So I don't know if someone can, let's say, monitor and just alert me.
I can tell you, say that there is a question in the Q&A session.
Okay.
Section.
Yeah. Perfect. Should I try to share screen just to make sure everything works?
Oh, so wait, let me allow you to share screen because that's the point we always forget. Yeah, now it should be okay.
As a remote teacher, I definitely can sympathize with that.
Yes, looks like we're all good.
And you can see everything, including my...
Yes, and your mouse pointer too.
Okay. Actually, there is, maybe I can actually open up a Q&A box. It'll block some of my screen, but probably it's okay. Can't seem to resize it, but maybe that's okay. You don't see the Q&A box on my screen, right?
I think I don't, no.
Okay, so you just see the background.
Yeah, just the presentation.
Okay. All right, well, that sounds good. Seems like there's no technical issues.
So finally, after almost a year of lockdown, we managed to learn to master the Zoom.
I still am working on it, but getting pretty good. So how's everything? Are you all nearing return to normalcy?
I think not quite. We'll still have maybe a month to go with the under some restrictions, and then it seems that next term, which starts end of April, would be pretty normal.
Oh, in the sense of in-person instruction?
I think so. Yeah, that's my feeling. Yeah, because the UK plans, I think, to lift all restrictions in the end of June, and they'll have substantially lifted at the start of May. So
I see. Well, yeah. So for us, the spring quarter it starts, I guess, similarly April, and yeah, it'll be completely remote.
Oh.
But I think the trajectory here seems like we'll hopefully be on track to have in-person instruction in the fall. I'd be surprised if we don't by then. I mean, that's already in September, October.
I know that Scott Aronson is very worried about the vaccination process in the United States, and I just wanted to ask, how is it going?
Well, I guess it depends on who you ask and where you and it's geographically very non-uniform. That's my understanding. At my institution, people are starting to get vaccinated pretty rapidly, is my impression. Including I believe students, postdocs, teachers. When I talk to some colleagues from different states, they're very surprised that that's going on. So I think it's something that it's not controlled at the national level; it's controlled at local levels, and there's varying degrees of progress depending on exactly where you're at.
I see.
Oh, I see. There's 49 participants.
Yeah, I think so. Yeah, I think we can wait maybe for 2-3 minutes more. That's what we usually do. Okay. I have recently heard really at some academic seminar there was a joke that all events at Oxford start 5 minutes later to the agreed time because there's exactly the time difference between Meridian and Oxford longitude. Oh, yeah. Mm-hmm.
Are these all Oxford students?
No, I think we have. I think we have quite a lot of people from all over the world for this event, because it's online and we advertise it wherever we can. And I think, yeah, so if our participants want to indicate where they're from, please like drop a message in the chat. We'd be like really happy to see what's the geography of today's talk. Yeah, so we have Oxford, Cambridge, Cairo, Egypt, UCL, Berkeley, Cambridge, Cambridge, Armenia, Pittsburgh, Columbia University, Mexico, Bristol. Oh, guys, we're like so happy to see you here.
Yeah, this is wonderful. But you know, I've tried to cater this to undergraduates. So is that the right? So these are undergraduates from these different places.
I think so. Like guys, I think most of you are undergrads. Or yeah. Anyway, like undergrad knowledge wouldn't hurt any graduate level who doesn't do topological quantum computing. People from Poland, California, even there is India, Slovenia. Wow.
Wow. Very cool.
Macedonia, St. Petersburg.
Now, if there are questions, are people going to post them in the chat box or the Q&A box?
No, so yeah, dear participants, if you have a question, there is a question answers like tab in at the bottom of your screen. So please
That's
post
what I
questions
should look out
there.
For questions.
Yeah.
Okay.
Not in the chat.
So I'm going to close the chat box.
I don't know. I have a feeling that it's always warm in California, but is it warm there right now?
It's sunny. I wouldn't call it warm, but it's, you know, I can go outside right now, probably in a t-shirt and feel maybe reasonably comfortable. I have a long sleeve shirt on right now. It's pretty nice outside.
Okay, I think we shall start. Let me then say a few formal words and then we proceed. Right, yeah. So welcome everybody to the last event of our society in this term, last event also for the current committee. And today we have Professor Jason Alicea from Caltech. He has obtained his, I think, PhD degree from Caltech back in 2007. Then he became an assistant professor there. And also he's a full professor at Caltech. And he's a condensed matter theorist who is interested in exotic phenomena which appear at the interplay between quantum mechanics and topology. And I'm just like saying what I've read in the internet. And he's in particular interested in the such phenomena which host such particles as anions. And if I'm not wrong, if I'm not mistaken, we are really lucky today because I have heard many times about topological quantum computing, but I still have a very vague idea what is this. And Professor Jason Alicea will tell us today not only what is this, but about some ways to design experiments allowing us to obtain it with the components we already have and which we well understood. And that's the topic of today's talk. So maybe I'll stop here and.
All right, well, thank you so much. Thanks for having me here. I didn't know I was actually the concluding speaker, so happy to be the person to wrap up this series. So, you know, as was just said, I'm going to give you an introductory overview of a bold idea called topological quantum computing, which aims to build quantum computing hardware in a manner that's intrinsically scalable and immune to errors. Before I go further, I very much encourage questions. The more questions, the better. I'm going to try to keep an eye on the Q&A box, but please don't be shy. And if I don't respond to a question, it means I didn't see it. So just alert me if that happens. All right, so I'm going to begin this talk by going back 6 decades to 1959. So in that era, computers were giant room-sized machines. And in that era of room-sized machines, Richard Feynman, shown on the right, gave his classic lecture titled "There's Plenty of Room at the Bottom." In that lecture, Feynman was speculating on opportunities that would arise if we could miniaturize technology to an extreme degree compared to what was possible at the time. I think he was, literally imagining circuit elements whittled all the way down to the size of atomic scales. So one quote from that lecture, Feynman said, "There is nothing that I can see in the physical laws that says that the computer elements cannot be made enormously smaller than they are now. In fact, there may be certain advantages." So the certain advantages is the interesting part of this sentence. There's some obvious advantages to miniaturizing technology, making devices more compact, improving speed, minimizing heating, and so on. But there's a more subtle advantage that relates to the fact that, if you're thinking about atomic scales, quantum mechanics is unavoidably the choreographer of physics at those length scales. And if you can make your information itself quantum mechanical, then there are naturally new opportunities that could arise. Feynman himself alluded to those opportunities already in 1959, and we've come to appreciate the opportunities there more deeply in the years that followed. So let's imagine that we, follow Feynman's vision all the way to its extreme, and imagine that you encode a single bit of information in terms of two possible states of an atom. Okay, so those are zeros and ones, which are quantum bits, which I'll call qubits. So those qubit states, again, could represent, let's say, two different spin configurations of the atom, two different orbital states, and so on. Now, we know that quantum mechanics allows for some inherently non-classical behavior. If this was a classical bit, your bit could either be in 0 or 1, but quantum mechanics allows for superposition. This qubit can be simultaneously in the 0 and 1 states. If you have two atoms, you have two qubit states, and you have yet additional richness that's possible. Here you can have an entangled superposition of those two qubit states. So in an entangled state, it's impossible to specify the state of one qubit independent of the state of the other. For example, 0, 0 plus 1, 1 is a famous example of a so-called Bell state. So it turns out that if you take advantage of those uniquely quantum features of superposition and entanglement in the way in which you perform computations, there are certain classes of problems that you could solve far more efficiently than you could in any conceivable classical machine, even the most powerful supercomputers that exist now, or could conceivably be built in the foreseeable future. So the applications include things like cryptography, simulating nature, designing new drugs, advancing artificial intelligence, and many, many other applications which we're still in the process of discovering. So people have been working on this problem for a long time, and a natural question that you might ask is, why can't I buy a quantum computer yet that fulfills all of this grand potential? Nowhere on the internet can you find an Intel Core Quantum qubit entangled processor. So the reason that you can't yet buy a quantum computer is that quantum information tends to be fragile and difficult to control. So these atoms never exist purely in isolation. There will always be noise that's acting without your wish for it to do so on your qubit states, and that noise can easily corrupt that quantum information. So that's the main bottleneck that we face in building scalable quantum computing hardware, at least via the conventional approach. So, faced with this dilemma, one very natural route forward that you might pursue is to figure out a way to improve your qubits, shield them to whatever degree you can from environmental noise, get sufficient control over those qubits, and then use ingenious quantum error correction schemes that have been developed over the years. So then, it's a very sensible way forward, and that's what typical approaches to quantum computing are doing, and for instance, in the context of superconducting qubits, ion traps, and so on. So I'm going to focus on a completely different route in this talk. Namely, suppose that you could figure out a way to encode and manipulate your quantum information in a way that was immune to noise in the first place. Okay, so that's the basic idea behind topological quantum computing. You don't try to get rid of noise, you try to encode your information in a way that it simply doesn't matter. All right, so in order to introduce the concept of topological quantum computation, I'm going to back way up and just think about the basic problem that condensed matter physicists are trying to solve. So roughly speaking, the goal of condensed matter is to understand quote unquote large scale properties of matter. Size scales that we typically think about are much larger than atoms, but small compared to astrophysical distances. Now, in that broad length scale regime, we essentially know the quantum theory of everything. Here it is in almost its full glory. This looks like a mess, but actually the physical content is rather familiar. You have some electrons, you have some ions. Those degrees of freedom have some kinetic energy encoded in the first line, and those degrees of freedom interact via Coulomb forces as described on the second line. There are, of course, other ingredients that you might wish to incorporate, things like spin-orbit coupling, coupling to electromagnetic field, and so on. But more or less, this is their quantum theory of everything, up to some perturbations that you can include if desired. Now, the crucial thing to observe is that the underlying laws of physics that give rise to that Hamiltonian are well understood, and they have been for many decades. Nevertheless, finding the behavior that emerges from those known laws is a highly non-trivial task, and will basically, I think, never stop yielding interesting scientific questions to pursue as long as people are around to ask the question. So the inherent reason why finding the behavior that emerges from these known physical laws is challenging and interesting is because we're dealing with a very large number of degrees of freedom, typically on the scale of 10 to the 23. Now, a naive approach that you might try to take in order to solve this problem is to start from something that you can actually solve exactly. You might start, let's say, from the properties of a single atom. If this was a hydrogen atom, you could solve it in a classroom setting. If you go to more complex atoms, it's harder to solve analytically, but maybe with the aid of a computer, you can get a good understanding of that single atom problem. So then, armed with that understanding of 1 degree of freedom, then you can try to introduce a second degree of freedom. So that 2-atom problem is more complicated, but maybe with sufficient effort, you can solve that problem exactly as well. And you can try to introduce a 3rd atom and so on. So you will rapidly run out of steam if you pursue this exercise. But what you might hope is that before you run out of steam, you get enough insight into the generic behavior of the system that you can anticipate what the properties look like when you go to a macroscopic number of degrees of freedom. Now, fortunately or unfortunately, depending on your perspective, that approach of building things up one at a time to try to go from few degrees of freedom to many degrees of freedom is almost always misleading. So Phil Anderson, shown here, introduced this famous phrase, more is different, to nicely summarize the situation. More is different basically is indicating the qualitative difference between the behavior of a few degrees of freedom compared to many degrees of freedom. So more is different is really a pervasive concept that applies all across science, not just in physics, but biology, sociology, and on and on. So what I'd like to do now is give you one of my favorite visually striking examples of more is different in the context of actually birds. So birds are actually a quite interesting physics system, it turns out. What I'm going to show you now is two videos, one of a single bird flying, and then next to that a video of a large number of birds flying together. All right, so here's one bird. This is the behavior of many birds. Now, if you think about one bird, there are lots of interesting questions you could ask about a bird, things like intelligence questions, anatomy, biology, and so on. But if you stare at this, wonderful video on the bottom, when you put large number of birds together, there are qualitatively new behaviors that emerge. As I mentioned, this is actually an interesting physics problem. Bird flocking is an interesting example of a physics physical system that evades the so-called Merman-Wagner theorem, which you may have heard about. So these, these birds are behaving almost like a single collective organism. It turns out that, the behavior of one bird on one side of the flock can be intimately correlated with the behavior of a bird arbitrarily far away. All right, so this is, again, I think a really nice visual example of more is different. Actually, ever since I learned about some of the physics of bird flocking, I never look at birds the same when they're flying above me in the sky. It's quite amazing. All right, so now let me, so that's a visually striking example of more is different. Now let me take this back to the setting of matter. So a single atom, I want to loosely associate with a single bird. And this problem of many atoms that interact with each other via our quantum theory of everything, that is loosely akin to this massive flocking pattern that you've just seen. Okay, so similar to the new kinds of phenomena that appear for many birds, one can naturally expect that there's going to be many new phenomena that arise for this collection of atoms. Now in this atomic problem, the behavior is vastly richer and more subtle because the organization of electrons is choreographed by none other than quantum mechanics in all of its fascinating properties. All right, so lots and lots of remarkable emergent phenomena can appear in collections of atoms. This is basically the field of condensed matter physics. What I'm going to do now is focus on probably my all-time favorite example of an emergent phenomenon. I think one of the most striking manifestations of more is different that I've ever come across. And that's the emergence of new kinds of particles that have more exotic exchange statistics compared to those microscopic constituents that ultimately give rise to any piece of matter that you ever care to think about. Let me now remind you of the concept of exchange statistics. Exchange statistics describes how wave functions transform when you take some collection of identical particles and swap their positions. Okay, so for example, suppose that I start in some initial wave function psi, and then I take two of these particles and swap their positions. The exchange statistics for those particles tells me what happens to that wave function after that exchange. So this is really one of the basic pillars of many particle quantum mechanics. It's easy to take for granted, but this property is really extremely fundamental. And if you think about it, it underlies most condensed matter phenomena that we see in nature, ranging from the existence of metals, insulators, superfluids, superconductors, and on and on. In terms of exchange statistics, nature allows for only a few different classes of particles. Two that everyone on this call is no doubt familiar with are bosons and fermions. So if you trade two identical bosons, then your wave function just remains invariant. Whereas if you were trading two identical fermions, then the wave function gets an extra overall minus sign. Now, it turns out that all fundamental particles that exist in our universe necessarily are one or the other, either bosons or fermions, and at the level of fundamental particles, there's no room for anything else. It's actually an interesting topological reason for that, which I won't get into. But interestingly, this does not quite exhaust the full set of possibilities that we can find in the laboratory. Because if you take large collections of conventional bosons and fermions, allow them to interact, new phases of matter, exotic phases of matter can form that give rise to new kinds of emergent particles called anyons, which have much more exotic exchange statistics compared to those microscopic constituents. So anyons can be further subdivided into two categories. The simpler variety are so-called abelian anyons. These are already quite fascinating objects. If you take two abelian anyons and you swap their positions, then the wave function actually gets a complex phase factor e to the I theta that's intermediate between plus or minus 1. We call these abelian because abelian basically means commuting. And if you were to perform multiple exchanges amongst abelian anyons, the order doesn't matter because the wave function will just acquire the product of these complex phase factors associated with each exchange, and the order in which those phase factors are accumulated makes no difference. Interestingly, there are lots of experimental platforms nowadays for abelian anyons. The so-called fractional quantum Hall effect is a wonderful platform for this physics. And in fact, just in the last year, we've, for the first time, we now have experimental confirmation that this kind of exotic exchange statistics even actually exists in the laboratory. So my discussion today is going to center around the second kind of anyons, so-called non-abelian anyons, which are much more exotic and elusive compared to their abelian cousins. And it's these things that are the workhorse of a topological quantum computer. All right, so in order to find non-abelian anyons, you have to stabilize certain kinds of exotic topological phases of matter. And for the purposes of this next part of the discussion, let's assume that you found such a system in the laboratory. So what I'll do now is describe the basic characteristics of non-abelian anyons that make them special, and then tie this discussion into topological quantum computing. So one of the fascinating features of non-abelian anyons is that as you start to populate them within your topological phase of matter that supports these emergent particles, the system actually gets an exponentially growing ground state degeneracy. So for example, if you introduce a pair of non-abelian anyons, then your system might have two degenerate states to choose from. If you add a second pair of anyons, your system might have 4 states to choose from. Adding a third pair of anyons grows that degenerate set of states to 8, and so on. So that hopefully sounds like a pretty weird feature, but I want to caution that ground state degeneracy by itself is not so spectacular. In particular, let's think about a comparatively trivial problem. Suppose that you have just some insulator, electrical insulator, that has embedded in it a bunch of free spin-1/2 degrees of freedom. And by free spin-1/2, I just mean a spin that energetically doesn't care whether it points up or down. So in this completely trivial problem, every time you add a new free spin-1/2 to the system, you will grow the ground state degeneracy by a factor of 2 and get a very similar counting to what I just showed you for these non-abelian anyons. So that's indeed true, but I want to starkly contrast the kinds of ground state degeneracy that you get for these free spin-1/2 degrees of freedom and the kind of ground state degeneracy you get for non-abelian anyons. One important distinction is that in the case of these free spin-1/2s, I can, at least as a matter of principle, perform local measurements to decipher where my system actually lives among those that set of ground states. So for example, you could imagine performing a magnetization measurement to tell whether each of these individual spins pointed up or down, and therefore tell which of these states your system was populating. By contrast, in the case of non-abelian anyons, there's no local measurement that you can perform even as a matter of principle, whether you probe the system in the vicinity of these non-abelian anyons or elsewhere, that gives you any information about which of those systems, which of those states your system is actually populating. A closely related property is that for these free spin-1/2s, that degeneracy is by no means robust. So you could easily partially or completely lift all that ground state degeneracy by applying a magnetic field, which let's say preferentially, which favors, let's say, spin up over spin down for these electrons. Once again, in stark contrast for these non-abelian anyons, this degeneracy is immune to arbitrary local perturbations, whether those perturbations arise from magnetic fields, electric fields, chemical potential variations, disorder, and so on, provided those perturbations are not sufficiently severe so as to destroy the non-trivial phase of matter that allows these non-abelian anyons to exist in the first place. Okay, so I can see that there's a question. Let's see, why there's no local measurement to decide the non-abelian state. Well, this is okay. It's an important question. It's a question that I can't really answer because it's a defining characteristic of non-abelian anyons. They have this property that they give rise to a special kind of ground state degeneracy, which you can't identify individual members of via local measurements. Maybe I could try to say a little bit more about that in just one second. But I think to really answer that satisfactorily, I would need to go into much greater detail and go through, let's say, specific models that allow you to see in detail, that property actually exists. Okay, but for now, I'll note that by comparing trivial degeneracy that you get from free spin-1/2s and the degeneracy from non-abelian anyons, what we can infer is that these anyons must carry some kind of unusual zero energy degrees of freedom. And those unusual zero energy degrees of freedom are very different from spin flips, right, which are the things which span the ground state degeneracy for these spin-1/2 degrees of freedom. And instead, these zero energy degrees of freedom span a special kind of ground state degeneracy consisting of states that are all locally indistinguishable from each other. And maybe in the context, given the question that I was just asked, the simplest kind of zero energy degree of freedom corresponds to something that you may have heard of. It's called a Majorana fermion zero mode. And you can really think about a Majorana fermion zero mode as being half of a fermion in a way that can be made precise. And in that particular context, there would be, if you take, let's say, a pair of non-abelian anyons, together they share a single fermionic state. But half that fermion is localized here and half that fermion is localized here. So if you wanted to know whether, let's say, there was a fermion populating that state, it wouldn't be sufficient to just look here or just look here. You would have to do a non-local measurement that knows about both of those non-abelian anyons at the same time. All right. And so local measurements basically that information is completely hidden from you. So I hope that maybe provides some additional insight. Okay, so that's one of the first key features of non-abelian anyons. They give rise to the special kind of exponentially growing ground state degeneracy consisting of states that you cannot distinguish via local measurements. Let's go a little bit further now. Suppose that you initialize your system into one of those locally indistinguishable ground states, which I'll call psi sub I, and then perform a swap of two of these non-abelian anyons. Now, those are indistinguishable particles, just like bosons and fermions. Nevertheless, the act of exchanging those two non-abelian anyons transforms this state in a really profound way. So this initial wave function that we started from won't just acquire a plus or minus sign, as it would if these were bosons or fermions, nor will it acquire a complex phase factor, as it would if these were abelian anyons, but instead exchanging non-abelian anyons fundamentally transforms your quantum state. So more precisely, that exchange will rotate your system from one member of this locally indistinguishable ground state manifold to a different state in that manifold. All right, so that rotation is quantified by a so-called braid matrix Uij, and the content of that braid matrix is just to specify precisely how your exchange got rotated in that ground state subspace. All right, so there's another question: how is a Majorana fermion an enneon? I would not say that a Majorana fermion is an enneon. So this is indeed a very tricky nomenclature issue. So enneons, they carry some unusual zero energy degrees of freedom that span this ground state degeneracy. And in the simplest kind of non-abelian enneon, that ground state the zero energy degrees of freedom correspond to objects that can be described by Majorana fermion operators. But I don't want to conflate the zero energy degree of freedom that gives rise to the degeneracy with the enneon itself. So the zero mode is a property of the enneon. Okay. All right, so this is the remarkable phenomenon of non-abelian exchange statistics. So we call it non-abelian because non-abelian basically means non-commutative. If you were to perform multiple exchanges of these non-abelian enneons, the order now matters. The final state you end up in is very sensitive to the sequence in which individual exchanges were carried out. And you can see that here, just basic property of matrix multiplication. Matrix multiplication is, except in very special cases, non-commutative, and the non-commutativity of matrix multiplication implies non-commutativity of braiding operations. All right, so that's a second basic feature of non-abelian enneons. They display the remarkable phenomenon of non-abelian exchange statistics. The third key feature is that they obey so-called non-trivial fusion rules. This means that if I take two non-abelian enneons and bring them together in space, they can always combine into at least two different kinds of particles. And to put this property in perspective, you might think about, let's say, an electron and a positron. So those are elementary particles that are antiparticles of one another. If you bring them together in space, there's no question they will annihilate each other. But for these non-abelian enneons, there's never a unique answer. Bringing two non-abelian enneons together might cause them to annihilate, or you might be able to have those two particles combined to give some completely non-trivial quasi-particle type. All right, so those are the three key aspects of non-abelian enneon DNA. They encode locally indistinguishable ground states. They display non-abelian statistics and non-trivial fusion rules.
I'm sorry, can I have a question?
Yes,
so,
of course.
Is this fusion result probabilistic? That's what you mean. So each time you kind of has some probability of happening of annihilation or another particle occurring.
Very good question. Okay, so the In general, it's probabilistic, and the probabilities will be determined by basically how you prepared the system and what kind of operations you did in between. So for instance, did you braid things around each other and so on? And that's actually important and related to the next thing I'll say. All right, so these features, I think, from a basic science point of view are quite fascinating on their own. And I think by themselves very much warrant experimental pursuits of this physics in the laboratory. But as the focus of my talk is on topological quantum computing. I mentioned that these are also the workhorse of topological quantum computers. And so there's not only basic physics motivation here, but technological motivation. All right, so these non-abelian anyons are the workhorse of intrinsically fault-tolerant topological quantum computers. So let me sketch the basic idea of how a system like this could be useful for quantum information processing. So first of all, this space of locally indistinguishable ground states is a very nice place to encode quantum information. So for example, if you had 8 states, that's enough Hilbert space to encode 3 qubits. The first state you might associate with, let's say, the 0, 0, 0 state, second state 0, 0, 1, third state 0, 1, 1, and so on. Now, the key feature is that the same property that makes it difficult for the observer to perform local measurements and tell which of these states your system was realizing also makes it difficult for local environmental noise to corrupt that information. All right, so by using these non-abelian anyons, we figured out a way to encode quantum information in a way which is by default hidden from the environment. So that's not the only benefit here. We have not only a fault-tolerant way of storing information, but we also have a fault-tolerant way of processing that information. And that arises from non-abelian statistics. So from this point of view, you can view these UIJ matrices, which again told you exactly how your system got reshuffled within this ground state subspace in response to an exchange. Those matrices can now be viewed as quantum gates, which process those qubits in very precise ways that you as the user control, depending on which of those particles you swapped around each other and in what order. And finally, at the end of the day, you would want to read out that information. And here's where non-trivial diffusion rules come into play. After you've performed some prescribed set of quantum gates to carry out some algorithm, to read out the answer at the end of the day, you could bring these particles together. And by detecting exactly what particle type they entered at the end, that allows you to infer the state of your qubits, which was otherwise hidden from you when those anyons were all mutually far apart from one another. All right, so that's the basic idea behind topological quantum computing. Initialization would work by basically generating pairs of non-abelian anyons and moving them far away from each other, giving you this ground state. Information processing arises from these braiding operations, and readout involves bringing those particles back together and figuring out what they fused to. Okay, so there's a question. If the ground states are indistinguishable, but the states possess non-trivial exchange statistics, in which measurable variable do the ground states distinguish then, and how can we differentiate between them? Well, that's related to fusion rules. So actually, maybe I can be more precise about this. If you want to read out the information stored in these qubits, you have to do either one of two things. You have to either perform a non-local measurement, right? So as I mentioned before, there might be, let's say, a single fermionic level encoded between 2 spatially distant non-abelian anyons. And if you're able to perform a measurement on that scale, then you can infer the occupation and therefore get some information about where your system was in this ground state manifold. Alternatively, you could intentionally give up on that local indistinguishability, which is basically a fusion process. You can bring those particles together, and which basically lifts this ground state degeneracy. And once that ground state degeneracy is lifted, you have your system. You open up your system to local measurements. Local measurements can now give you information about which state your system is populating, and in doing so, you could infer the state of your qubits. Now, that's a kind of general thing, and I could, if there was a given physical context in mind, I could be more precise about what kind of measurement and manipulation processes you would actually bring to bear in this problem. But in a nutshell, that's the basic idea. Any other questions for now? All right. So this idea that I've just introduced to you was invented some years back by my colleague Alexei Kitaev. And for that work, he was one of the inaugural winners of the so-called Fundamental Physics Prize, which is a really nice prize to get for several reasons. One, you get this cool plaque. You get $3 million award, and you also get to attend an award ceremony hosted by Morgan Freeman. And in case you think I'm joking, here's, I hope you can hear this, here's Morgan Freeman announcing Alexei's prize.
For his work in this tradition using topological phases to create robust quantum memories and fault-tolerant quantum computation.
So there it is. I'm not making this up. And just as an aside, I've heard people say fault-tolerant topological quantum computation, I don't know how many times in my physics career, but never with the panache that Morgan Freeman brings to this. I wish I could say it like that. All right, so the $3 million question in this field was already solved by Alexei, but the $1 billion question is outstanding, and that's how do you build the hardware to bring this beautiful idea to experimental life? So nowadays, there are actually many different approaches that experimentalists are pursuing in the hunt of non-abelian anyons and eventual topological quantum computing hardware. There are two broad categories of platforms that I'll mention. The first I'm going to loosely describe as intrinsic realizations. Here, the basic principle is that you, let's say, have some system of electrons or spin degrees of freedom, whatever, and you rely on some non-trivial Hamiltonian dynamics to stabilize that phase of matter, to stabilize a phase of matter that hosts non-abelian anyons. So there's some serendipity that's required in that approach, but since serendipity has led us to at least two different kinds of promising platforms, one involving the so-called fractional quantum Hall effect, and another involving exotic phases of magnetic materials known as quantum spin liquids. Now, there's a second class of proposals that are pursued nowadays that remove serendipity from the equation. These are what I'm referring to as designer realizations of non-abelian anyon platforms. And basically, these designer approaches seek to emulate physics of so-called topological superconductors, either in one dimension or two dimensions. So these topological superconductors have a really nice property that they're very simple toy models that you can write down to understand in great detail all the non-abelian anyon features that I sketched on the previous slides. At the level of classroom style calculations, everything is exactly solvable, free fermions, and you can really go to town. Now, the downside of those toy models is that it's very difficult to find intrinsic realizations in nature. But the key advent is that people have figured out lots of very clever ways of combining well-known and well-understood ingredients to basically force the electrons into realizing one of those topological superconducting states. There's a very, very long list of blueprints along those lines that combine ingredients like semiconductors, superconductors, ferromagnetic atom arrays, magnetic fields, and a variety of other systems. And so the idea is that you take these well-understood ingredients, you piece them together in just the right way, and if things work out as you hoped, you will get a non-abelian anyon platform out, kind of by design. So this is really an amazing development that has taken place over the last decade or so, and most of the experimental activity has indeed over that time period focused on these designer realizations. All right, so here's a slide that illustrates where essentially we are in this problem and where we'd like to go. Nowadays, people are spending most of their effort experimentally pursuing the question of anyon detection. Right, so that's the most basic thing you would want to do is convince yourself that you've made a phase of matter that indeed harbors non-abelian anyons. It turns out that this is a trickier problem than people had anticipated, and I think many people would be quite cautious about whether or not we've unambiguously identified non-abelian anyons in pretty much any of these platforms. Now, where we'd like to go in the long run is, ascend all the way up to this mountain and build scalable topological quantum computing hardware, and, revolutionize technology. Obviously, there's a very, very wide gap between where we are now and where we'd like to go. But what I would like to emphasize in the last part of my time here is that there's plenty of room in the middle of this journey for really fascinating physics discovery. So I'm going to give you two examples of some of my favorite applications that we can hopefully explore in the laboratory as we work our way up towards applications. So the first involves the fabrication of a prototype topological qubit. And this is actually an ongoing effort that is very much on the radar of both industry and academia, and particularly on the industrial side. Microsoft is very heavily pushing this direction as we speak. Now, you might ask, how much can you actually learn by studying just a single prototype topological qubit? So I just noticed that there's a question, why is this approach called topological? Well, so, topology is a branch of mathematics that quantifies properties that are invariant to smooth deformations. Classic example, people talk about, let's say, a sphere being topologically distinct from a torus, because, by deforming a sphere, you have to, to deform a sphere into a torus, you have to do something drastic. You have to, poke a hole, and that's not something that you can do via smooth deformation. So the topological aspect of quantum computing really refers to the insensitivity to noise. The quantum information itself is immune to local perturbations. You can, deform the Hamiltonian somewhat. You can add noise, and your information should remain resilient. Similarly, the way in which you process that information is also inherently topological and invariant to smooth deformations. Here, I can emphasize that there's not a unique way in which you can trade a pair of non-abelian anyons in space. There's actually an infinite number of trajectories that you can follow to do that. And the key property is that these braid matrices U don't care about the details of which trajectory you took. They care about only global properties of which anyons went around which other anyons. And so that's another aspect of topology appearing in this quantum information setting. Both the way in which we store and manipulate information is immune to smooth perturbations. Okay, so I hope that answers that question. All right, so let me go back here. So I was asking what could you really learn by studying one prototype topological qubit? Certainly, if you were dealing with conventional qubits, you wouldn't make a splash if you made a single new conventional qubit. Right? But in the case of this topological qubit, you can stand to gain an enormous amount of mileage, basically because you can verify by studying just a single topological qubit all of the essential features of non-abelian DNA that I showed you earlier, and you can also hopefully gauge how promising that technology will be for more long-term applications. All right, so I'm going to spend a little bit of time showing you the kinds of experiments that you would want to do to really unravel the physics of a single prototype topological qubit. All right, so it's well beyond the scope of what I'm going to do here to tell you about the inner workings of this topological qubit design that I'm showing you here. I'll just mention that what I'm showing is one example of a topological qubit design in the designer approach to the problem. So these orange regions are meant to represent some superconducting degrees of freedom. The gray thing underneath is some semiconducting wire. And these black lines here, those are meant to illustrate some electrically tunable valves that allow me to control anyons within this qubit. Okay, so in this starting configuration, I have 4 anyons indicated by these circles here. Now, together, those 4 anyons encode a single logical 0 and 1 topological qubit state. And one thing I can do here is I can close these electrically tunable valves, which has the effect of, let's say, bringing those anyons together, fusing them together, in which they can form one of 2 possible particle types that I'm sketching here by either blue or green circles. Now, in this particular apparatus, you can detect whether a blue or green particle emerged from this fusion process in a rather standard experimental measurement scheme, so-called charge sensing. And by measuring whether you got blue or green circles out, you would be able to identify whether your qubit was in a 0 or 1 state. All right, so again, I'm not my goal is not to tell you how this works, but basically just to tell you what kind of information you could get from this kind of measurement. And here there's two key things that you would be able to learn. One, you would be able to measure the fact that, detect experimentally the fact that these pairs of non-abelian anyons can form one of two different particle types. And in detecting that property, you also establish a way to do a qubit readout. Because again, with how those things fuse correlate with whether your qubit state was in a 0 or 1. And if you can't do readout, then it's hopeless to move any further along that mountain. All right, so here's another interesting kind of protocol you could imagine doing on a single topological qubit. So I'm resetting this device. So I have, once again, 4 non-abelian anyons giving me a protected 0 or 1 qubit state. Now, another thing you might hope to do is quantify the resilience of this qubit to local environmental noise, right? Which is, again, one of the key features that makes this, first of all, that makes non-abelian anyons special, and from a basic science point of view, and also of interest for long-term technological applications. All right, so noise, we have made no attempt to completely shield the system from noise. Noise is still there, but we're trying to encode the information in a way that noise simply doesn't matter. Now, here's why I should say that no topological qubit will ever be perfect. The kinds of introduction I gave you before assumed ideal situation. And in practice, this local noise will eventually, over some hopefully long time scale, succeed in corrupting that quantum information. Okay, and in this particular geometry, there are ways of measuring the lifetime of that quantum information. And suppose that you measure that, and it's hopefully long time scale, let's say a second. Now, it's not really clear, how do you know whether that 1 second time scale was associated with some non-abelian anyon physics and immunity to local noise versus just maybe the noise was just not doing that much in the first place. So to really nail down that protection is arising from non-abelian anyon properties, you can imagine doing the following thought experiment: make the device bigger. So when you make this device bigger, you bring the anyons farther apart, and the farther and farther you bring these non-abelian anyons, the more and more immune to local noise they become. So in the example I gave before, where there was a single fermionic state that was shared between the two of these, that single fermionic state gets pulled in two pieces by larger and larger distances, and therefore it gets harder and harder to tell by any local measurement any information about that fermionic state. So, but what you should be able to find here is that by pushing these non-abelian anyons farther apart, your lifetime of quantum information actually grows exponentially. And if you were to recover that exponential growth of the lifetime, that's really the smoking gun fingerprint that you've stored information in this intrinsically resilient fashion. All right, so if you were to successfully perform this experiment, you would validate the existence of a intrinsically robust topological quantum memory, because your 0 and 1 that you stored here would have exponentially long lifetime. I should say that my favorite experiment, the one that I would most be excited to see done in the hopefully not too distant future, is this one. I think this would be really, really cool, not only because it's giving you some very basic feature of non-abelian anyon physics, but would go a long way to ascertaining the promise of this physics for applications. So the last thing I'll do is take this single qubit, where once again I have 4 non-abelian anyons, and decorate it with this vertical leg. Just introduce another superconducting region with some additional valves. By tuning these valves, electrically tunable valves, we can actually swap the positions of these inner non-abelian anyons. I can, let's say, adjust these 2 valves to bring that anyon here, swap these 2 to bring this anyon to the left-hand side, and then modulate those 2 to bring the anyon up and to the right. Again, I realize this is cryptic. My goal is just to tell you what kind of experiments you could do. So here, you've managed to swap 1 pair of non-abelian anyons. And if you started in the 0 qubit state, after that swap, you should rigidly rotate your qubit into an equal superposition of 0 and 1. And here's the rigidity aspect, the topology aspect here. You could imagine doing that exchange 1,000 different ways with 1,000 different rates, and you should get precisely this rotation, independent of how you did that. And if indeed you found that after this exchange, you got an equal superposition of 0 and 1 states, that would be an experimental demonstration of topological quantum information processing and non-abelian statistics. All right, so that's what you could learn from studying a prototype topological qubit. I wanted to say one more thing, but maybe I should ask if, I think maybe I'm a little over time. Should I just wrap up here?
I think we still have time.
Okay.
Maybe up to 1 hour.
Okay, perfect. All right, so this will be actually pretty brief. I would definitely like to leave as much time for questions as I can. Another of my favorite destinations en route to topological quantum computing is to imagine performing analog quantum simulation with anyons, with non-abelian anyons. And so, to put this perspective, we started out by, putting a large collection of atoms together. We relied on this Moore's different paradigm. We assumed that those atoms formed some exotic topological phases of matter that allows us to nucleate these non-abelian anyons. So we could now think about, Moore's different squared. I can now think about these non-abelian anyons as new degrees of freedom, bring them together, allow them to interact, form some kind of anyon soup, and ask what kind of new phenomena I can realize within that collection of interacting non-abelian anyons. And what you might imagine here is that, given the very non-trivial structure that's already built into the property of those kinds of emergent particles, it might be, there might be certain kinds of phenomena that you could much more naturally describe with a collection of interacting anyons compared to a collection of interacting conventional atoms. Indeed, there's lots of neat physics that you can imagine engineering by controllably bringing non-abelian anyons together and allowing them to interact in ways that you will hopefully be able to control in the possibly distant future. One of my favorite examples is that you could imagine bringing together some collection of non-abelian anyons and emulate the so-called Sachta-Vieh-Kitaev model. I don't know if this is familiar to anybody, but it's a really neat model that has close ties to black holes, quantum gravity, and quantum chaos. And a few years ago, I worked on some project with a former student, Aaron Chu, who came up with a kind of tabletop implementation of that Sachta-Vieh-Kitaev model by basically bringing a bunch of non-abelian anyons together. Now, another thing which I think is really neat to contemplate is using those non-abelian anyons to get even better anyons out. So you can imagine nucleating some new kind of topological phase that's even more exotic than the one that we started from, that has quote unquote better anyons. And when I say better anyons, I mean a kind of non-abelian enyon whose non-abelian statistics allows you to perform a denser set of qubit rotations compared to the ones that you might have started from. And so, okay, so there's a question. Let me see what the question is. Hang on a second. Would you recommend a student to start an experimental PhD in Majorana-Zero modes in their applications as qubits? Is it not too risky if in the end it turns out topological quantum computing will never take off? Well, am I qualified to answer that question? That's very much a personal decision. I would say that, the physics of Majorana-Zero modes is, particularly on the experimental side, it's in the category of high risk, high reward. I think one could certainly have a very successful career in physics, studying Majorana-Zero modes experimentally, not just in PhD, but potentially for your entire career, even if you never manage to make a topological quantum computer. And this is one of the beautiful things about this field, in my opinion. Every stage of the journey from non-abelian enyon detection all the way towards application is paved with just opportunities for profound physics discovery. And so, for example, if during your career you manage to unambiguously confirm non-abelian statistics, but didn't make it any further up the mountain, that might be like a Nobel Prize worthy discovery on its own. And so I think you should not measure the success of this program as, necessarily whether we make it all the way to the top of the mountain, but, how many of the exciting milestones along the way can we achieve? And I don't have the prescience to be able to tell you how far we'll make it and when, but we do need people that are bold and willing to take on these challenging projects in order to to make progress. There's another question from the quantum topological memory. Is there a study, or can you tell us about the efficiency of storage and retrieval expected? Well, there's lots of theory projects that have studied lifetimes of topological qubits and detection schemes. Should you trust those theoretical studies? Maybe, maybe not. I mean, experiment has the final say, and I think we really need experiment to tell us how good these qubits are, and whether theory is accurately modeling them.
I think maybe let's finish like with the talk, and then, because it seems that we have like a lot of questions just popped up in the question answer section.
Okay, yeah, sure. Well, I am pretty much done, so this is maybe a great time to just conclude. So hopefully you got a sense in this talk for what topological quantum computing is about and what non-abelian anyons are. I emphasize that nowadays we have lots of different experimental avenues along which we can pursue non-abelian anyons, both in intrinsic and designer platforms. We're still working pretty hard in this field on anyon detection, and hopefully this will be settled maybe by some of you listening in the near future. I highlighted some interesting opportunities along the way. The nearest term, by far the nearest term thing I discussed was prototype topological qubit applications. Again, this is something that people are working very seriously on right now. Quantum simulation with anyons, that's much farther in the future, but I think conceptually very interesting. And finally, hopefully in my lifetime, we can start to see applications realized. So I started with a quote from Feynman. I'm going to end with a quote from Feynman, who said, I am telling you, I think this is from his same Plenty of Room at the Bottom lecture, I'm telling you what could be done if the laws are what we think. We are not doing it simply because we haven't yet gotten around to it. Similar sentiment very much applies to everything I've said here. The laws of physics appear to, as we know them, allow for non-abelian anyons and topological quantum computing. We need to just bring all this to experimental life. So that's all I was going to say. So maybe I'll turn back to these questions. Okay, so there's a question: have you done any work on topological semimetals, Weil fermions, Dirac fermions? What do you think of using topological materials as a platform for quantum computing? I haven't worked on topological semimetals myself. Certainly, well, not in 3 dimensions anyway. Topological materials are most certainly a promising platform for quantum computing, even topological quantum computing. I'm working on this actively in actually multiple different guises. The topological materials angle has been very fruitful for designer application, the designer realizations of non-abelian anyons. There's a very long list of proposals that exploit topological materials for non-abelian anyon physics. In fact, this whole designer route grew up in the context of topological materials. So the very first engineered or designer route towards non-abelian anyons that was introduced in the context of topological insulator superconductor hybrids. So this was really classic work by Fu and Kane. So anyway, a big fan, and I think there's lots of interesting things to do there, both theoretically and experimentally. Next question: why are experiments hard to perform, and why are people still cautious at the anyon detection stage? Okay, so experiments hard to perform. Okay, let me see how I should answer that question. There are some experiments that are not necessarily hard to perform. What's hard is to get the experiment to do what you want it to do. And so there can be all sorts of complications that arise. You know, for example, let's take the most well-studied approach, which was due to Roman Luchin and Company and Yuval Oreg and Company, the two classic papers that showed how you can get, in principle, non-abelian enneon physics by combining semiconductor wires with superconductors and subjecting that system to a magnetic field. Now, you know, on theory, it's very, very clear. The theory is, you know, very simple. You know, it should certainly be possible to get non-abelian enneons in that setting. But in an experiment, you know, you never know. It's you know, often very hard to say whether the theoretical models that you're using to describe a system are actually accurate theoretical models. And there's all sorts of things that can go wrong. You know, you can have disorder is you know, one very common culprit that can complicate things. You know, physics of interfaces between a superconductor and semiconductor can be very subtle, and you know, the magnetic field can do funny things that you might have not included in your zeroth order modeling. And so I think the hard part is not necessarily building the devices or making at least certain kinds of measurements on those devices, but convincing yourself that you've actually entered the phase that you are trying to realize. And you know, there have been experiments reporting signatures of non-abelian enneons in these kind of engineered devices for nearly a decade now. And the reason people are still cautious about those, at least many, probably most of those experiments, is that the kind of signatures that people have been using traditionally, namely, you know, electrical transport techniques, the signatures of non-abelian enneons can be mimicked by boring degrees of freedom, and that's been the really challenging thing to disentangle in the context of designer heterostructures. So hopefully that gives you a sense for, you know, what's hard and why people are cautious. Okay, so next question. Can I imagine non-abelian enneon pair behaving similar to a Bell state made from 2 qubits separated by a large distance? Well, I mean, you can certainly imagine, well, you know, the hope of, you know, the ideal topological quantum computer would allow you to perform arbitrary unitary rotations on arbitrarily many qubits. And so, you know, certainly you should be able to get an entangled Bell state from 2 qubits. If you can't do that, then, you know, that's you won't get very far. So certainly one can imagine that. And, you know, you would ideally generate such an entangled Bell state by performing some prescribed series of braiding operations, possibly in conjunction with measurements. All right, next question, can you describe on simple system, how can you make a non-local measurement of some observable? Yes, so non-local measurements are traditionally done with interference experiments. So in the context of quantum Hall realizations of non-abelian enneons, there's this really nice idea for, you know, taking electrons from a lead and then fragmenting those electrons into fractionalized degrees of freedom that then braid around some collection of non-abelian enneons in some interferometer. And you know, that interferometry is a non-local measurement, you know, that tells you something about a collection of enneons that could even be mutually far from one another. So interferometry, I think, is the main non-local measurement that people have thought about. All right, so next question. Would you make any guesses of what timescale we might expect to see successful non-abelian enneon detection and prototype topological qubit research? Yeah. If you asked me 5 years ago, I might have said, you know, maybe within 5 years. That turned out not to be the case. I think it's really hard to say at this point. You know, what's becoming very clear is that, you know, from 10 years of experiments on hybrid designer non-abelian enneon platforms, the simple detection schemes are not necessarily the ones that we really want, because they can be ambiguous. So, you know, we're still really just, we may be, you know, not that close to well, first of all, in order to do topological qubit research, you had better, know with a very high degree of certainty that you have anyons in your device. And you better be able to, reliably generate those anyons. Before you can do that, I think, this is going to be pretty distant. How close we are, it's really hard for me to say at this point, because the farthest, the most sophisticated proposal in terms of material science are these nanowire proposals, as I mentioned, where you slap superconductor on the semiconducting wire and apply a magnetic field. If we figure out, we meaning experimentalists figure out, truly unambiguous detection schemes, maybe one can envision anion detection becoming a reality within possibly even a year or two. And prototype topological qubit, I mean, it depends on too many factors that I can't really foresee. Nowadays, I am keeping a very open mind, thinking about different platforms, even if it means kind of going several steps back compared to where we are with semiconductor wire-based hybrid designs. And because who knows whether whether the issues there will be sorted out and in what time scale. But at least, the thing that makes me excited about this field is that there are many angles that one can try to ascend this mountain along. It's not a single path, there's many paths. All right, so there's another question. Does the retracted Nature paper 2 days ago make the topological quantum computation further away from realization? Any examples of experimental platforms to search Majorana fermions that could be more realizable? Well, so I hopefully somewhat answered the second question. Indeed, there are lots of experimental platforms apart from semiconductor nanowires. One that I've been thinking about, which is a bit of a dark horse for sure, are magnetic materials that we hope realize so-called quantum spin liquids. But if you let's say look at postings on the preprint server, the archive preprint server, not quite daily, but there's routinely new ideas for how to get Majorana modes apart from semiconductor wires that seem quite promising. Again, I'm thinking about others as well. And this retracted Nature paper, to be honest, I didn't see this as nearly as big a hit as to the field as some of the media has made it out to be. I mean, that Nature paper, I was cautious about even well before I learned that there was going to be a retraction, and I think most people were who follow this field. I think even before that retraction, it was already clear that one has to be very careful about claiming unambiguous non-abelian anion detection. All right, so it looks like the last question is braiding of anyons relevant to the topological quantum computing. It's not only relevant, it's central to the whole enterprise. So braiding of anyons is how you would perform the quantum algorithm. So I'll repeat something I said before. The quantum algorithms in general have 3 stages: initialization, some sequence of gates, and then readout to get the answer at the end. Initialization happens by generating your non-abelian anyons in prescribed ways that initialize your system into a definite state that you decide on at the outset. Then the information processing, in the ideal situation, proceeds via some sequence of braiding operations. And then once you're done with that quantum algorithm, then readout proceeds by bringing those non-abelian anyons back together to read out the state of basically to read out the answer. So I hope that addresses the question.
Yeah, can I also have 2 questions?
Of course, yeah.
So, but I think they're kind of related. So in the very beginning of talk, you said that there is some topological reason for why there are only fermions and bosons with elementary particles. Could you please tell where we can learn about it more, or briefly explain? So I never thought that elementary particles is something topological.
Yeah. Okay. So I can tell you the argument. So suppose that, which I could draw here, but I don't. But suppose you had 2 particles and you would like to exchange them, right? And you want to ask, what phase factor did the wave function accrue under an exchange? At least what statistical phase factor, robust phase factor was acquired under that exchange. So if you can think about instead of thinking about that single exchange, suppose that we do a double exchange. So basically square that process. So, a double exchange like this is topologically equivalent to a trajectory where one of the particles remains fixed and the other goes all the way around the first one. So if you think about, let's say, the particle world lines, you can imagine deforming the world lines in such a way that one of the particles stays fixed and the other goes all the way around. Now, we live in a three-dimensional universe, for better or worse. And if you take one particle, if you fix one particle and take the other one all the way around, you could smoothly deform the trajectory of that moving particle without it ever coming into contact with this central fixed one, to the point where it actually didn't move at all. So I can try to illustrate that. So maybe I start with this guy, but then I bend it upwards, and then eventually I shrink it down to nothing. All right, so that tells you that two exchanges must be equivalent to doing nothing, at least in terms of some robust statistical phase. And so if you square root the identity, then you can get a plus or minus sign. And so that's those are the two possibilities that we know exist for bosons and fermions. And the only thing I relied on there was the fact that for three-dimensional particles, I can take that double exchange and distort it to nothing.
Thank you. And maybe the last question is for everybody who are maybe interested in learning more than in more depth of the topological quantum computing, the underlying mechanisms, what could you advise to read?
Now, it depends on what aspect you are interested in. So there's a really, really nice Reviews of Modern Physics article from Chaitin Nayak and company. That's a bit dated. I mean, I forget when it appeared, but it's that article predated a lot of the designer realizations that dominate experimental activity nowadays. But in terms of the basic concepts, that's a wonderful place to read about it. There's Kitaya's original paper, Fault-Tolerant Quantum Computing by Anyons, I think it's titled. Another great resource. If you wanted to read up on the more modern designer approach to non-abelian anyons, this topic is reviewed all the time. Actually, there must be 20 different reviews written by various people, including myself. I wrote one. I forget. Probably around 10 years ago now, which is again a bit dated, but nevertheless, I think for kind of basic concepts, it can be a nice place to learn about some of these toy models that allow you to see in very simple settings how non-abelian anyon physics can emerge. There are many subsequent reviews that focus more on, let's say, nanowire-based proposals. Yeah, so those are some examples.
Okay, thank you. Thank you very much. I think we have a comment in the chat saying, thank you very much for this inspiring talk and answering the questions. And I think indeed we have never had in our talk so many questions and all of them answered. Yeah, it was.
That's wonderful. Well, thank you very much for that.
You really did. I think it was really enlightening. I think given some hope for people.
Well, thank you so much. It was a lot of fun, and it was really awesome that I could talk to people from all over the world. I guess one of the few advantages to the pandemic.
Yeah.
More connected. All right, thank you all. Really was a lot of fun. Thanks for having me here.
Thank you very much. Have a good day, a good Friday there.
Okay, you too. Bye, everyone.